Hey, good morning, everybody. I must really love this class, making videos in the early morning. How are you? I just wanted to help you out a little bit today. Asynchronous today. What I'd like you to do is just not adding a lot of work or anything. I know some people are taking the SAT and some people are not, and we have different amounts of responsibilities today. But I would like to just ask you to do page 11. I'm going to redo this sample here, talking about it. And then I'd just like you to try a very similar one here on page 12, number 2. Another very similar one, number 3. And then number 4 is similar as well, except it does add in this one extra challenging idea about what would happen about halfway down. So 2, 3, and 4 are all doing full transfers. We just ask you stuff at the top, stuff at the bottom. But this one here is asking halfway down. So I'm going to model number 1 again. I think we did get through the whole thing in class, but I'll address the halfway down thing, see if we can figure that out. So to go over this again, if you need some help. We have a mass up high. I just put VI as 0, meaning it's not moving up here. So we do these where, you could have movement at the top, but we do a lot of times you're really just not moving. It's all potential. Then it slides down to the bottom and it loses all of that height and it gains velocity, just like my little ramp demo, trading height for velocity. So what's going on at the top? It has PE because it's got H, it's got height. So it's got mgh. We can figure out that number pretty easy. It's not moving, so 0 joules of kinetic. At the bottom, if we're all the way down at the bottom, now you have lost all of your height. So this would calculate to 0, PE. And KE, it is 1/2 mv squared, but sort of the way we would figure out how fast it's going and what that KE would be, because we can't calculate it with the final velocity. We don't know that. So the key is at the bottom, the kinetic energy is going to be whatever it had in the form of potential at the top. This is the idea of conservation of energy. You know what? Let me write the proper formula, and because the whole idea is mechanical energy at the beginning equals mechanical energy at the end. And what does that mean? It means PE plus KE at the beginning will equal the total combined PE plus KE at the end of whatever we're talking about. That's conservation of energy. So what's happening is with this example is by not moving at the beginning, this is 0. And then by not having any height at the end, this is going to be 0. So they're still equivalent. It's just whatever was PE is going to become KE because we have a nice full transfer. It does get a little trickier when you look at some other specific examples. So I guess let's do the problem. And again, I think I did this one in class. I didn't know if we finished properly and perhaps we rushed, and this will allow you to go back and check it out, So let's see here. So we got to do an MGH at the top. So 10 times 9.8 times 7, 686. And I do remember that number from class. So this is 686 joules. That is the PE at the top. That is like the total energy now for the whole thing. So what's going to happen is as you slide down to the bottom, that's what KE is going to equal at the bottom. And then we can pull the V out. That's my expression. So what's going to happen at the bottom? So now we know PE at the top. KE at the bottom is going to be 686. We're ignoring frictional forces. Have I answered the questions? Okay, pretty much. And then what is the speed? And then we just need this kinetic energy at the bottom and pull the velocity out. It's hidden in there, right? 1/2 mv squared. So you take that 686 and you say that equals 1/2 m, that's 10 in this case, v squared. Since it's easy enough in my head to do half 10, I'll just say 686 divided by 5 and then square root what I have. Let's do this. 686 divided by 5, square root answer. Yeah, 11.7 meters per second. Was it 11.7 meters per second? Okay. Now, just to address that halfway down thing, when we say halfway down, we literally mean half of the height. So if this object was to be at, this height right here, it's halfway down. It does have some PE still, but it's been moving a bit, so it does have KE. So we can still figure out these numbers and how fast it's going. So this is this little extra tidbit. If you can get this part here, oof, we're in good shape. So what would happen? Let me talk about halfway down. Maybe I'll kind of, so halfway down, you don't have a full transfer going on, but you do have a split right in half. So halfway down, what's PE halfway down? Well, halfway down, my drawing's not perfect here, but that would be what height? Wouldn't that be 3.5 meters? So you do an MGH, 10, 9.8, 3.5. So this was like the total energy. If you're halfway down, you have half of that still has potential. And what's the other half? It's got to be converted to kinetic. So when you're halfway down, you're really splitting that total energy number right in half. Let me just do the math and just check that it's half that. It's got to be. I don't know why I'm checking, but 10 times 9.8 times 3.5. Yeah, it's 343, right? Half of that number. So this is 343. And your energy, your mechanical energy is always your combination of your KE plus your PE. And that has to be the same before and after. So if that's your PE, 343 joules, and there's a total of 686, how much is KE? The same number, 343, right? Because they're half and half when you're halfway down. So that means KE must also be 343. And then just pull the velocity out of that number. So you'd say 343 equals 1/2 mv squared. You can do this. You can do it. Come on, we can do this. We can do this. We can do this. Take the 343 number, divide by 5, square root answer. And thank goodness we got a slower number, because if at the bottom it's going 11.7, I'll buy 8.3 halfway down. I like that. So I get 8.3 meters per second. This whole part right here, it is actually pretty important. It'll help us out with roller coaster ideas and like the last part of this. But this wasn't really part of this original problem. I think it's in number 4 there. All right, pop into extra help later. Oh, wait. Don't know if I'm going to have extra help later because I'm teaching full schedule at Old Japan. Email me if you have any problems. I'll help you out. All right, and I'll see you when I see you. I got to readjust the agenda. All right, later.